Hello hackers and welcome back. In this video we're going to make a setup using Qemu and GDB to debug the Linux kernel. Now I have already compiled my own Linux kernel using the Linux source tree. You can do this as well. I will provide a link to a website, kernel-newbies.org. It is a very famous website among people who are interested in learning about the Linux kernel and stuff like that. So I will provide a link to it, and probably I will couple this video with a blog post discussing in details everything you need to do to be able to use Qemu and GDB to debug the Linux kernel. So starting from building your own custom Linux kernel and configuring it, to building Qemu with the target system and connecting the GDB stub in Qemu to a GDB instance to remotely debug the Linux kernel. Although the steps to be able to compile your own custom Linux kernel is very well documented in the kernel-newbies.org, and almost everything about Linux is very well documented, and mostly all of your questions will have answers by the community. But anyway, I will provide the steps you need to take for that in the blog post. So before we start, I want to discuss several points here. Don't mind this tiny note over there. I can see it. Anyway, so I want to talk about the different Linux kernel file images. Now, over time, the Linux kernel had different file images, and all of them are very useful. So starting from the kernel executable, the kernel binary executable that is booted, to an image file containing all the debug information that we need. So right here I'm inside the directory where I've compiled my own custom Linux kernel. So if I went to boot and executed the file command on this bz image, we'll find it is a Linux kernel x86 boot executable image. So this is the kernel as an executable binary. And on the other hand, if I did file on VM Linux is also a file that you will obtain after compiling your own custom Linux kernel. We see that it is a statically linked. It is an ELF 64-bit statically linked with debug information and not stripped. So this is the Linux kernel with debug information and simple. So obviously this is the file that we need to attach to GDB to have all the samples that we need to be able to trace over and strip through the Linux kernel code. So these are the two files that we need. bz image is the Linux executable. This is the one that we're going to fire up in Qemu. This name has history. It was originally image, and then it was compressed with zlib. Although there are other compression algorithms can be used to compress the Linux kernel. And then B as in big Z image, because obviously over time the Linux kernel grew up larger and larger, and actually the Linux kernel is the largest code base, so this file is very big. And people might say that B indicates bzip2 compression, but that's not true. It is just bz image. Alright, and as I said, we have the VM Linux. Now that's one thing. When you compile your own Linux kernel, you get this file, VM Linux. If I went to boot, I'll find a VM Linux with Z. Now this is the same file but compressed. So if I do file, we'll find again it is a boot executable bz image. But there is a difference. This file, this image file, VM Linux with Z. Now you're going to find me saying it this way, VM Linux with D, because I don't know how to say it, VM Linux. Anyway, this image is the VM Linux, so it is the kernel, but stripped and has boot capabilities and decompression capabilities. So we can actually use this file image in Qemu to boot the Linux kernel, as we'll see. I will demonstrate both using the BZ image and the VM Linux, and both of them will work just fine. I guess that's all what we need for the first point. Now, let's talk a bit about Qemu. Qemu is yet another great open source project, and the first thing we need to understand about Qemu is that it is not a virtualization software. It is an emulation software, meaning Qemu does not use your hardware to virtualize, to give you a VM, a virtual machine. It actually emulates software. So if I went to the Qemu folder, and I guess it's in build, nope, it's in target, yep. Here we find here we find a couple of target systems that Qemu can emulate. So we have Spark, we have MIPS, we have x86, and ARM. So you can emulate an architecture that's not necessarily instruction compatible with the host running Qemu. In other words, I can emulate ARM system on my x86 machine. Qemu will do this just fine, and one thing about that is that if you want to run quote-unquote a VM in Qemu, this is actually slow, and you better use a virtualization software for that, because it doesn't make any sense to emulate a full-blown system. Although I know people who use Qemu to make an environment for gaming, which is absolutely insane. But anyway, what you want to do is to specify the target that you want to build, that you want Qemu to emulate, and you could do this by adding a target list compiler option, and you choose x86, 64, or whatever. I will also provide a link to the documentation to Qemu. So you can choose your target list, whether it's ARM, Linux 64, or 32-bit. And Qemu also has a ton of other options to use to give you a full system, but we're going to stick to our minimum options to just boot the Linux kernel. Alright, now let's actually boot the Linux kernel using Qemu. So in order to do this, we need to provide at the very least these two options, a kernel and an init.rd image. Now the kernel, of course, you give it the path to the BZ image, which, as I sort of mentioned, is the Linux kernel as an executable binary, and an init.rd or a RAM disk image. Now, in order to understand what an init.rd means, let's try to execute it without an init.rd and see what happens. Alright, so as we see here, we ended up in an error, and before trying to understand what this error means, unable to mount a root file system, let's talk a bit about what does it take for the Linux kernel to boot successfully. Alright, so we have the BZ image, which is the Linux kernel executable, right? And there's also two other components that the Linux kernel needs to give you this system, the full-blown Linux system. And the most important one is a RAM disk, an initial RAM disk, or what we call an init ramfs. Now, the initial RAM disk is an initial root file system that is mounted at boot time, so that important binaries like the init process would be executed, and along with other shell scripts. So this is the function of the RAM disk, is to be mounted as an initial root file system at boot time. So it will be able to execute crucial binaries that your system needs. And after it finishes executing these binaries as root, it looks for the real root file system, which is this one, the root file system. So if the init ramfs didn't find this root file system to mount, it will throw you to a recovery shell with a set of commands, a very limited functionality, giving you a chance to maybe mount the root file system manually. So for Qemu, you might need three options: a kernel, an initrd, and a root option to give it the root file system, which is the SDA1 or whatever you have in your system. But since we're only interested in booting just the Linux kernel, so we need at the very least two options, the kernel and an initrd. So let's close this one and try it again. Alright, given it the initrd command and a path to the RAM disk.image. Now, in order to make a RAM disk in your system, of course, you have to boot to your newly custom compiled kernel. So depending on your distro, this command is different. In my case, I'm running Debian, so the command is init make ramfs, and I've already made one. So let's execute it with the initrd and the kernel, so these two options only, and we'll find that the Linux kernel will boot with no problem. Okay, so the kernel has booted successfully and we are in the init ramfs shell. So if we did help, these are the set of commands that we can run. And as I said, it gives us very limited functionality because it complains here that there is no root device. And in order to give it to the Qemu instance, we need to provide a root parameter. But anyway, that's all what we need to successfully boot the Linux kernel. Now let's connect this with GDB. And in order to do this, we need to provide a tick S and a tick capital S. Now this is to connect to the GDB stub, and this is to tell the kernel to stop and pause booting the Linux kernel until a GDB instance connect to it. And I will also provide an option to redirect the output to this console, and that would be it. So let's run, and as we see here, it is paused and the kernel won't boot until we connect to it. Now, as I said, to be able to remotely debug the Linux kernel, we need the Linux kernel symbols. So we have, and you will have in your own Linux kernel custom build directory, you would have the VM Linux, and this is the one that we need, and GDB will start reading the symbols from there. And what we want to do is to connect to the GDB instance over the port number 1234, and we have successfully connected. Now we can now start debugging from there. So for instance, I'm gonna put a breakpoint on start kernel, and let's hit continue to see booting. And obviously we can't see any output because I forgot to add the no graphic option. And alright, so let's do this again. Target remote 1234, and alright, let's hit continue, and we see here it will start booting the Linux kernel. Alright, so obviously this did not hit our breakpoint. This is because we have to provide a no KASLR option to the Qemu instance. Now, of course, you know what ASLR means. Now there is a kernel ASLR, and our breakpoint wasn't hit because the kernel performs ASLR as a security measure. And what we need to do is just provide no KASLR, and we should do this again. Now, as we see here, we have our breakpoint hit. So now we can disassemble start kernel. I'm going to enable the text user interface. We can trace through the source code, and there is a very nice thing about GDB as well, is that you can specify your breakpoints by the line number over the file that you're executing from, and obviously we are now executing from the main.c. So again, disassemble, let's see, kernel init, and there you have it. We can do all sorts of stuff from there. And I should also mention that there is a GDB script you can attach to your .gdb init file. So let's cat.gdb init. You have to add this GDB script. It already exists. This is one good thing. Also, another good thing about compiling your own Linux kernel. So again, if we navigate it to the Linux kernel directory, we see there is a scripts directory. So this contains all sorts of helper scripts, semantic check scripts for submitting batches, and GDB scripts. So what you'd want to do to use these while specifically debugging kernel modules is to add it to your GDB init. Alright, so I hope you're not confused with all these terminals. Alright, so once you add the path to this helper script to your GDB init file, you will have access to these commands. Let's try to execute, let's say, simples. You'll see here that it tries, it loads the simples from VM Linux, and that's it. If you have configured, again, if you have configured your custom Linux kernel to build and compile kernel modules, you will have it also reading and loading different kernel modules that are built in your custom kernel. So I guess this is everything I wanted to talk about. And here we have the kernel will boot freely. So for the sake of integrity, I said that we could boot the Linux kernel by using the VMZ, the VM Linux with Z file. Now let's try this. We get it from boot, VM Linux C5Z, and we see that it booted just fine. This is because, as I sort of mentioned, the VM Linux with Z is the kernel executable, but with the debug information stripped, and it also has boot and decompress capabilities, so that you can use it to boot your Linux kernel. And as I said, the kernel that is shipped to your distro doesn't come with a VM Linux. It comes with this compressed VM Linux. That's a better way of saying it. It comes with this VM Linux compressed. And as I said, it has boot and decompression capabilities so that you can boot from it. And I'm pretty sure there is a way to decompress this compressed VM Linux. I just don't know how. So you can look it up. So that pretty much wraps up everything I wanted to discuss in this video. I really hope you've learned something from it, and see you next time.
Mine is endless. You put me in a dark, solitary cell, and to you, that's the end. To me, it's the beginning. It's a universe in there. There's a world in there.